In the last lecture, we discussed the design of fiber optic link. So, if you look back, up till now what we have done in this course is just discuss the basic components which are needed to establish a link between 2 points. So, initially we discussed the medium, which is the optical fiber. Then we talked about the sources like LEDs and lasers. Then we talked about photodetectors. Then we talked about optical receivers. So, these are the basic components which are required to establish a point-to-point communication link. Today we are going to discuss essentially the advancements which have taken place in the fiber optic communication due to advancements in laser technology, the advancements in fiber technology. So, these things which we are going to discuss now onwards, these are what are called the modern advances which have taken place in the area of fiber optic communication. And one of the major things which has happened in this area is the development of a system what is called the wavelength division multiplex system, or in short it is called the WDM system. Now, what is the origin of this WDM system? If you recall, when we discussed the point-to-point communication link and the sources which are used for this and the detectors, we found that the detectors and the sources, they have a bandwidth limitation. What that means is that these sources cannot be modulated beyond a certain frequency. If you go to today's technology, it will be very difficult to modulate an optical source beyond about 10 gigabits per second, and the same thing on the receiver side, it will be very difficult to detect a signal which has a data rate higher than 10 gigabits per second. So, it then looks that due to the limitations of the electronics or the electro-optic converters which are going to be used on either side of the optical fiber, we will not be able to increase the data rate beyond about 10 gigabits per second. In the laboratories, people are investigating the data rates of 40 gigabits per second, but these are still at the experimental stages. If you look at the deployment of the systems, these systems are essentially less than about 10 gigabits per second systems. Later on, we will also see that due to the nonlinear effects which are present inside the optical fiber, it is difficult to increase the data rate beyond about 10 gigabits per second. So, that means if we establish an optical communication link and use one transmitter and one receiver, then effectively we can use the bandwidth of about 10 gigabits or 10 gigahertz. Let us now compare this number with the bandwidth which the optical fiber has. Because if you remember, when we started discussion on optical fiber, we had suggested that this is a medium which has a much larger information carrying capacity. We have seen that the optical fiber has a very large bandwidth because it has low loss optical windows, and effectively if you could make use of that bandwidth, then one can stuff a huge amount of information on the optical fiber. So, let us look at the low loss spectrum of the optical fiber, what we call as the transmission window, and this is the typical gain profile or the loss profile which you get for the optical fiber. So, here is the wavelength going from about 900 nanometer to about 1700 nanometer. And as we had seen earlier, there are two windows. The second window of optical communication, which is around 1300 nanometer, and the other window is around 1550 nanometer. That is where the loss is low. Also, now the advancement in the optical fiber technology has taken place, where even this peak is reduced significantly. So, we have essentially a window which can extend from about 1200 nanometer up to about 1600 nanometer, where loss is reasonably small. Even if we don't go into the reduction of this peak, we have the two windows, one around 1300 nanometer and one around 1550 nanometer. So if I see typically, this window would range from about 1270 nanometer to 1350 nanometer, and this window would range from 1480 nanometer to about 1600 nanometer. If I convert this into the corresponding frequency, typically we have a bandwidth here available, which is about 15 terahertz, and here about 15 terahertz. So a total bandwidth which we have, including these two windows, is about 30 terahertz. So when we are having the medium which can support effectively a bandwidth of 30 terahertz, if we use only one transmitter and one receiver, we can use a bandwidth of only 100 gigahertz. That means we are off by a factor of thousands in terms of utility of the optical fiber. Or in other words, if we use the optical fiber medium just for one channel transmission, then the system is highly underutilized. And that's what essentially is the origin of the WDM system. That can we do something now to exploit the bandwidth which intrinsically an optical fiber has. So if you could make use of these bands effectively, we should be able to get effective bandwidth of about 30 terahertz. Now initially, when the systems were designed, in 1310 nanometer window, and you may recall that this was the window because the dispersion was very low in this window. The material dispersion goes 0 around 1270 nanometer. So the systems were developed around this window. Later on, as the system lengths become longer and longer, even this difference in these two laws was significant, and then the window was shifted to 1550 nanometer. So this is the third generation system, this was the second generation system. Since initially the systems were already operating here and new systems started coming into 1550, for a while we could use both these windows, one channel of transmission in this window and one channel of transmission in this window. So simultaneously on one optical fiber, two signals were transmitted, one in 1310 nanometer window, other one at 1550 nanometer window, and both could carry the data rates typically of the order of few gigabits per second. So essentially what we have done is we have multiplexed now what is called in wavelengths. So we call this system as a wavelength division multiplex system. So we are now sharing the bandwidth which the optical fiber has, and both the channels can carry independent information on two wavelengths. So now if I look at the numbers, what this essentially is telling you is that the low loss window of the optical fiber, which is between 1.2 micron, which is 1200 nanometer, to 1.6 micron, that is 1600 nanometer, we have an effective bandwidth of about 30 terahertz. If you want to talk in terms of the communication channels, that means this bandwidth can support effectively 300,000 channels of 10 megabits per second. I use the number 10 megabits per second because if you want to have a video channel, that's the kind of bandwidth typically it would need for a good quality video. So that means if we can use the entire bandwidth of the optical fiber, we would be able to transmit 300,000 video channels on a single optical fiber, and that's a very huge capacity. So as we have been saying in this course, that intrinsically the optical fiber is capable of supporting a huge amount of information, and the limitation primarily is coming from the electronics which is used on either side of this optical fiber. So, now to exploit this bandwidth, which is 30 terahertz, there are two possibilities. Either we can exploit this bandwidth in time domain, that means we can share this medium in time, what is called the time division multiplexing. But in that case, then I would have to generate the pulses which would be of a duration typically inverse of this quantity. So, if I have a 30 terahertz bandwidth utilization, then we require a pulse width which will be typically few tenths of femtosecond. Femto is 10 to the power minus 15. So, 10 to the power minus 15 second, which is an extremely narrow pulse generation, and especially with the semiconductor amplifiers, it will be extremely difficult to generate these kind of pulses which are of duration 10 to the power minus 15 seconds. So, it immediately appears then that exploitation of this bandwidth of 30 terahertz is almost impossible in time domain, because we will not be able to generate the pulses which are as narrow as this. So, then the other possibility is that we should be able to use this bandwidth by dividing this bandwidth into frequency bins and transmitting information independently in each bin. And that's what essentially we do in what is called the wavelength division multiplexing, that in this case now we can access the bandwidth easily in the wavelength domain than time domain, and this is far easier in terms of optical communication, because as the laser technology has advanced, we can get now a very high quality laser at multiple wavelengths. Each wavelength can be modulated with different data rates, and simultaneously multiple wavelengths can be transmitted on the same optical fiber. So, due to this characteristic that this large bandwidth cannot be accessed in time domain, and the advancements which have taken place in the laser technology, essentially the wavelength division multiplex system came into existence. For a while, people were trying to see some other possibilities, like using nonlinear effects on optical fiber. Can we generate the systems? Can we go for coherent communication? But these options are far more difficult than simply transmitting multi-channel signal on an optical fiber. In that sense, the WDM systems are far more realizable systems than any other options which are available. So, what we do in WDM system, basically we divide the signal into multiple channels, or we have multiple carriers in optical domain. Each carrier is modulated by a data rate, maximum possible data rate, and all carriers simultaneously are transmitted on an optical fiber. So, initially when the two windows were used, we had one channel transmitted in 1310 nanometer, other channel transmitted in 1550 nanometer, and then we called this system as the WDM system, wavelength division multiplex system. However, as the time progressed, and as I told, since the laser technology is now far more matured and its spectral width has significantly reduced, one can essentially put multiple channels even within a window of the optical fiber. And then, since now the channels are closely packed, these systems are now called dense WDM system or DWDM systems. So, dense wavelength division multiplex system means within a band which is 1550 nanometer or 1310 nanometer, we have multiple carrier transmitted, and then ITU has given certain standards for placing these wavelengths within the spectrum. So what ITU is essentially specified is that within this window of 1550 nanometer, we can put multiple channels, each carrying the data rate of, let us say, 10 gigabits per second, and these wavelengths, just to avoid the clashes and interferences, they have to be on a fixed grid, what we call as the ITU grid. So in a WDM system, as per the ITU specification, we have ITU, which is International Telecommunication Union. We have a standard which is G.692. Now for this standard, the reference frequency is taken as 193.100 terahertz. This corresponds to essentially a wavelength of 1552.524 nanometer. And then the ITU has specified that every 100 gigahertz we can put another channel. So the spacing which is specified for DWDM channel is 100 gigahertz, which is approximately 0.8 nanometer at 1552 nanometer. So the ITU grid is equispace in terms of frequency. It is not equispace in terms of wavelength, because wavelength will depend upon the center wavelength here. The spacing will depend upon that. So every 100 gigahertz, essentially we have a carrier, and if we transmit the data of, let us say, 10 gigabits per second, the channel essentially will occupy about 20-30 gigahertz bandwidth. And then next channel, which is separated by about 100 gigahertz, it will not overlap with the spectrum, and we have a fair amount of isolation between different channels. So this is the specification which we have for what is called the DWDM system, dense wavelength division multiplex system. So once you have this, then a typical WDM network would look something like this. We have a transmitter which operates at certain wavelength, let us say lambda 1. And when I am saying a transmitter here, there may be a whole network behind this. That means the data multiplexed from various locations are multiplexed and brought to this point here. This data now is riding on a wavelength lambda 1. Similarly, I can have a time division multiplex data which comes from here, and it is modulating a source lambda 2. And like that, we have a sources, let us say there are n sources with different wavelengths, lambda 1, lambda 2 up to lambda n. Then we have a device here what is called the wavelength multiplexer or a power combiner, where all these wavelengths are essentially combined and you get one multiplex output, and this is given to the optical fiber. The system we are talking here still is point to point as far as the optical communication is concerned. You may have a complex network here, but the optical network, which is this, is still point to point. The whole multiplex data on different wavelengths is modulated and given to this optical fiber, and the signal travels on this optical fiber link. Depending upon the distance, you may require amplifiers, periodic amplifiers, because as we have seen earlier when we were talking about the design of a communication link, that invariably the signal distortion is not very large, but the signal to noise ratio goes below the acceptable value. So periodically you can put optical amplifiers. So if the optical amplifier has a bandwidth larger than the bandwidth of all together, then in one shot all these wavelengths can be amplified in the amplifier and the signal can keep propagating with periodic amplifications. It reaches on the other side where we have a wavelength demultiplexer. So the wavelengths are separated, lambda 1, lambda 2 and so on. And then you got your signal back, which is time multiplexed data, which is started from here. So this is the basic principle of the wavelength division multiplex system, that we have a complex time division multiplex data. This data rides on different wavelengths and the different carriers simultaneously go on an optical fiber. On the other side, different wavelengths are demultiplexed. So depending upon their destination, they will be separated, and then again you can recover your time multiplex data. So what is the advantage if you go for DWDM system? The DWDM system is far superior compared to what you could get from the single channel. Firstly, it is very clear that we have a capacity upgradation. And what do I mean by that is, let us say today we have laid the optical fiber and we have got a requirement of, let us say, 10 gigabits per second. So we can put one laser transmitter, one detector on the other side. We can send the information at 10 gigabits per second. Tomorrow, let us say our requirement increases to 20 gigabits per second. We don't have to change the link as such. Essentially, we have to add one more transmitter at another wavelength. Just multiplex the two wavelengths and send on the same optical fiber. Our system capacity is doubled. So just by adding more and more carriers, we can essentially upgrade the system to the desired requirement. And that's a very important characteristics of DWDM system, that without significantly affecting the existing link, you can upgrade the capacity of the optical communication link. The second important aspect of WDM system is the transparency. Let us say if we had a data which was time division multiplexed. So let us say initially we had a transmission of, let us say, 1 gigabit per second. And now we upgraded our capacities to, let us say, 2 gigabits per second in time division multiplex system. So the time slots are now reduced in size, and also the data is now multiplexed in time. So one requires a precise information of a channel or a signal in that time frame. This demultiplexing is far more complex. So when we upgrade now the data rates in a time division multiplex system, the whole timing information has to be reallocated, should be reworked out. Also, if you go to the long links where there are repeaters in between, then for a time division multiplex system, essentially you have to demultiplex the data, amplify, clean, regenerate the data, again put on the optical converter. So the whole process becomes very, very complex. Whereas if you have a multiple carriers in optical domain, the formatting which is used for each of this carrier is irrelevant. So one carrier might carry some data rate in time domain, another carrier may carry some another data rate in time domain. And when we go to amplifiers or in between stations, a particular wavelength is amplified without worrying about what is carried by this wavelength. So the whole information flow by using optical carriers becomes format independent, and that's why we call this as a transparency of the data formats, because irrespective of what data format you are using, essentially the wavelength is the one which is deciding the characteristics of the signal flow now. The same thing can be extended now to what is called wavelength routing. So earlier, when certain information packet has to go to a certain destination in time domain, what one would do, one would just take the bits, read the bits, find out from that what is the address for this packet, and then route appropriately that packet. So it requires essentially reading of the time bits. So when a fast data is coming in time division multiplex system, you have to first of all demultiplex this data, read the bits, find out its address, destination, and then put back the packet so that it can reach to proper destination. When we go to the WDM system, essentially the wavelength itself can be used as an address. So all that information which we wanted to send to a particular destination, we can label it by wavelength, let us say lambda 1. If another information block we want to send to another destination, we can label it at lambda 2. So now the whole routing of the information is just decided by the wavelength. So without really getting into the bits and reading the addresses, just whatever is coming on lambda 1 is routed to that particular destination, whatever comes from lambda 2 goes to other destinations, and so on. And this is significantly now faster, because in time domain, when we are reading the header of the packet, it requires some processing time. So wavelength routing would be much faster in optical domain than going to time division multiplex system. So it gives you an advantage that you can now route the wavelength by simply labeling the information by the wavelength. You can also switch the information from one wavelength to another wavelength. So it's possible that when we talk about complex networks, we'll see a little later, that information can go on a particular wavelength from one destination to another, but beyond that point the information cannot go on the same wavelength. So either the wavelength can be blocked, or you can transfer the information from one wavelength to another wavelength and the information can still keep flowing. So wavelength division multiplex systems have gone far beyond the simple point to point communication link which we discussed here. So here we are simply combining the wavelengths and sending on the optical fiber to increase the capacity. But with the enhancement of technology, advancements of technology, we have got now variety of devices in optical fiber which can do all these operations. It can do wavelength routing, it can do wavelength switching. So then if you ask now what is the requirement of a WDM system? Firstly, since we are now going to put a large number of wavelengths in a window, the total wavelength division multiplex signal will occupy a substantial bandwidth. If you are going to use a window which is 1550 nanometer, then we would require a fiber which has low dispersion in that window. If you have a large number of wavelengths, then not only zero dispersion in that, but dispersion should be reasonably low over the entire wavelength range which is used for WDM system. So we require now as a backbone for WDM system a dispersion shifted fiber for 1550 nanometer use, or a dispersion flattened fiber which can give you a very low dispersion over a very wide optical bandwidth. We will also require the tunable or the multi-wavelength lasers, also switchable lasers, because we can switch the information from one channel to another channel, and today's technology gives all this. But this is one of the important components which will be required for WDM systems. Then we require broadband optical amplifiers, because if the large number of channels are going to go on the optical fiber, the most efficient system would be if amplification of all the channels together is done simultaneously. So we are in search of the optical amplifiers which have large bandwidth, and these have now become possible, but they are again one of the important components for a WDM system. And then we require a large number of wavelength dependent optical devices. For example, we may require a wavelength filter, or we may require a wavelength dependent switch, or we may require a wavelength dependent reflector. So proper wavelengths are guided, routed, reflected. All those things can be done on specific wavelengths. So essentially for a WDM network as a whole, we require large number of wavelength division dependent optical devices. So component wise, if I now look at what are the components which we require, so what is the background technology which we need for a WDM system as a whole. So we will require the amplifiers. So the amplifier could be either semiconductor optical amplifiers, or they could be fiber based amplifiers, and in that we have EDFA, erbium doped fiber amplifier. We will discuss all these things in detail. Or we can have now an amplifier what is called the Raman amplifier. Then the devices which are used like combiner of different optical channels, dropping a particular wavelength or adding a particular wavelength, and if you want to do this dynamically, that means you should be able to configure these things. We require devices what are called the integrated optical devices, and in that we can have integrated optical switches or couplers. So integrated optical device essentially is IC version of an optical circuit. So if you create some kind of a optical guiding mechanism on a wafer, that will become an integrated optical circuit. Also we want to make the circuits on what the materials what are called the active materials, so that their characteristics can be changed dynamically. So integrated optical devices is one of the key components, right, in modern optical communication systems. Then we have the devices which are based on fiber, what I call the fiber Bragg grating devices, and these are extremely powerful devices in the sense that these devices are passive intrinsically and they are completely compatible with optical fiber. So these devices can perform various functions of wavelength routing and switching and dropping by a miniaturized component which is based on fiber. So in recent years, the fiber Bragg grating based devices have gained a wide popularity. Then we have the devices what are called the arrayed waveguide gratings. These are essentially like a planar structure which we have, which can again perform the routing of the different wavelengths and so on. So having understood now that for a WDM system, these are the vital components. Now we will look at each of these components in more detail. So first we will try to understand the amplifiers, then we will go to the integrated optical devices, then we will talk about Bragg gratings, and then we talk about some other aspects of optical communication. So, these topics essentially would fall in a broad category of advances in optical communication. So, let us take now the first device which we need is the optical amplifier, and let us go back to our original discussion of the fiber optic link design. Let us do a simple calculation. You remember when we talked about the link design, we had two aspects. One was the loss in the optical fiber, and other one was the pulse broadening of the optical fiber. The loss essentially is accounted for what is called the power budget calculation, whereas the broadening of the pulse, which affects the data rate, is essentially decided by what is called the rise time, and so we have a rise time budget for the communication link. So, let us now take a typical numbers which we can use for an optical communication link and try to see the power budget and the rise time budget. So, let us say we are transmitting the data rate of 10 gigabits per second. This is what I mentioned, we can go maximum to that rate, and let us say we want to have a BER of 10 to the power minus 9. Let us say we have a transmitter power about 10 dBm, and if you recall, this is already a very large power. Typically the power levels are about 0 dBm to plus 3 dBm, and the minimum power required for this BER is about minus 45 dBm. So, if you take a fiber loss of 0.3 dB per kilometer, then because of the power budget or because of the signal to noise ratio constraint, the repeater spacing has to be about 200 kilometer. We can do the calculation for the rise time, and we say that data rate is 10 gigabits per second, and if you use the dispersion shifted fiber, the dispersion on that could be, let us say, 1 picosecond per kilometer nanometer, and if you use a DFB laser, we can get the spectral width of the laser, which is 0.01 nanometer. So, we can get a repeater spacing which should be of the order of about few thousand kilometers. So, this calculation very clearly tells us that signal to noise ratio is the prime factor in deciding the location of the repeater. It also tells us that in the old systems, wherever the repeaters were placed, at that location, in fact, the signal to noise ratio was the one which has gone below the acceptable limit, but signal is not distorted to really a very high value. That means distortion of the signal was acceptable, but since we did not have any option, we used to put a repeater there and we used to regenerate the signals. So, if the signal to noise ratio is the problem at a distance of about 200 kilometer, then there is no point in putting a whole regeneration system there. Just a simple amplifier at this location would do. So, this calculation then essentially demonstrates that for long distance optical communication link, we do not have to put the repeaters over every 100 kilometer or 200 kilometer. A simple optical amplifier can be placed at that location and the signal can be sent over few thousand kilometers without actually installing a repeater. And if you remember, we had mentioned that the repeater is a expensive proposition. So, if you could reduce the number of repeaters on the link, then that is very desirable. So, this essentially makes now a case for an optical amplifier. So, we can send the signal over very long distances just by cascading the amplifiers, and then these amplifiers are what are called the line amplifiers. What are the possibilities of amplification in optical domain? We have two possibilities. One is the semiconductor amplifier, semiconductor optical amplifier as we call it, or it could be fiber based amplifier, and that is the erbium doped fiber amplifier. Let us have a quick comparison of these two. The semiconductor optical amplifier is nothing but a laser. If you recall, the laser intrinsically is an amplifier. By feedback, you can convert that into a source, but intrinsically, laser is a device which can amplify the optical signals. So, in fact, all that thing which we have discussed for lasers, that essentially can be used for creating an optical amplifier. And since we are now having sources which are in 1300 nanometer and 1550 nanometer, essentially we can create amplifiers in the same band. The semiconductor amplifier can also give you high power outputs, but the biggest problem of semiconductor amplifiers is it has a higher coupling loss. Signal is coming from the optical fiber, it has to be launched inside the semiconductor amplifier. After amplification, again the signal has to be coupled back into the optical fiber, and that gives you a significant loss. So, a semiconductor amplifier has a higher coupling loss from fiber to the amplifier and from amplifier to the fiber. This is integrable because this is going to be an electronic semiconductor device, and this amplifier also has high nonlinearities. The other option which has become very popular, which is the fiber based amplifier, an erbium doped fiber amplifier. This amplifier can only work in 1550 nanometer window. So, compared to semiconductor amplifier which could be any of the windows, the EDFA works only in one of the windows, which is 1550 nanometer. But it has a large number of advantages. It has a fairly low crosstalk. It can give high gain of about 25 to 30 dB. Also, it can handle high power. This is not very different than what this can do. But the biggest advantage of EDF is it is completely compatible with the optical fiber. In fact, this amplifier is built inside the optical fiber. We will see later how this amplifier works. But basically the same fiber, if you dope with a material which is erbium, you can create an amplifier inside the optical fiber. So, it has a low coupling loss, and that is a very desirable feature for an optical system. Also, it gives very low noise, and this is insensitive to polarization of the signal which is amplified by this amplifier. So, EDFA essentially offers many more advantages over the conventional semiconductor optical amplifier, and that is the reason this amplifier has gained popularity over last one decade. Only limitation as we see for this amplifier is that it has to work only in the window which is 1550 nanometer window. So, generically then what is the amplifier characteristic? So, generically we know in an amplifier what we need is something called an active medium, similar to what we have seen in laser. So, what we do in laser, we have a medium which can be pumped, the material can be excited, and then if the signal is incident on this, the stimulated emission would take place and the signal photons will get amplified in number. So basically what we are looking for intrinsically inside an optical amplifier is an active medium, a pump source which can excite this material, and a coupling mechanism from the optical fiber to this active medium and vice versa. So we have this optical input signal which is coming, it gets coupled to this active medium. When it propagates inside this, the pump power gets transferred to the signal power and the signal comes out in amplified form. So that is the basic requirement which we have inside an optical amplifier. So an active medium, a pump source and a coupling devices which can couple the optical fiber to this device and back. So essentially what we are looking for now, a material first of all which can have the energy levels corresponding to those wavelengths or frequencies which we want to amplify. So we have seen in laser that if you are having the difference in the energy levels equal to the energy of the photon, then the stimulated emission can take place and the photon flux is amplified. So firstly what we have to do is we have to identify the material which have proper energy level differences corresponding to the frequency of the signal which we want to amplify. And that's what essentially is done in this erbium doped fiber amplifier EDFA. So we have here the energy level diagram of erbium doped fiber amplifier. So what is done? We have the normal fiber, glass fiber. The core of this fiber is doped with erbium atoms. So we have a doping of erbium. So it becomes an ion. So 3 electrons of this erbium atom are gone. So that's why it is having a positively charged. So if you take the glass and dope with this erbium ions, then we have the energy levels which will look something like this. So as we have seen in terms of laser discussion, we have something called a ground state, then we have got excitation state, and then we have got another state here which we call as the metastable state, where the electrons can come and wait and then they can make a transition and they can give emission which could be stimulated. So by putting the erbium, essentially we have created the energy level system inside the optical fiber, and this difference between the metastable level and the ground level, this is in the range of 1550 nanometer. So this is the difference of the energy we are going to make use of in the amplification of the optical signal in the window of 1550 nanometer. So now the idea here is as follows: we excite the atom from this level to this level, and this difference corresponds to 980 nanometer. This difference from edge is 1480 nanometer to something like here, which is about 1550 or 1560 nanometer. So this band is fairly broad. It can go from about 1480 nanometer to 1560 nanometer. And this band is difference is 980 nanometer. So there are now two possibilities. One is we can pump this material with a 980 nanometer source. So it's excited to this level first. Then the lifetime from this to this is very small, of the order of about, let us say, microsecond. So very quickly the material relaxes to metastable level, which is this. Then within this level the system can relax to the lower energy levels which are more clustered here, and then the stimulated emission can take place between the lower end of this band to the ground state. So, since this band is very broad, there is a possibility that we can either pump material by transporting the electrons from this level to the higher end of this band, which is 1480 nanometer, or we can take the electrons to this level, which is 980 nanometer energy difference. So, erbium doped fiber amplifier can be pumped either by 980 pump source or by 1480 pump source. The 980 pump source is more efficient, it can give you more gain, also it gives you less noise, so on. So, 980 nanometer pumping is preferred compared to 1480 nanometer. Also, since 1480 nanometer pump is close to the signal wavelength, the separation of the signal and the leftover pump, as we will see, becomes more difficult. So, this is the basic material now we have identified, what is called the erbium doped glass, which has energy levels such that the 1550 nanometer signal can be amplified. So, we will continue our discussion on this amplifier, which has really revolutionized long distance optical communication, because now by using this very tiny device, erbium doped fiber amplifier, we can send the signals over hundreds and hundreds of kilometers.